Okay, so the talk is on quantized mereology, and I'm usually not very successful with presenting, comments of ways, so don't worry about yelling at me, and then I get drunk if I'm not clear. So I rather go slow and half through than moving and right at the beginning. So that is the quantized mereology, that's the plan. I'm starting with mereological information, relations of information. Then I will talk about mereological vagueness from an information theoretic perspective. Then I'm trying to argue that if you believe in the arguments I'm going to give, then you have to commit yourself to the idea that mereological information about vague objects will be quantized. So you have all the matters of quantum mechanics in the consequences. Then there's a good news in the sense that if you hate quantum mechanics because you don't like a complex number, you can do the same thing using the partitions of this set. So it turns out that what quantum mechanics does in Hilbert spaces can be done using the partition policy. So, and these are equivalent from the almost equivalent formulations. Oh, okay. So, and then in the end, I probably don't make it so far. But the idea is, why would this be useful for ontology in general? And the other point will be that whenever you have something which is a finite tree, which has finite amounts of leaves, of categories, then if you look at it information theoretically, then you will have n bits or 2 to the n bits in the ideal case. And whenever you have vagueness, you will have less than 2 to the n bits. And then the theorems kick in which commit you to being stuck with quantum information. So what I'm presenting basically is a simple kind of case. So where you have mereology, which is well understood, where you have 3 bits of information, and I'm trying to convince you that at least in the mereological case, it makes sense to think this way. But if you acknowledge it for mereology, or for the case I'm presenting, then you're automatically stuck with it for whatever more complicated cases there are. Okay, so mereological relations are relations based on the part-whole relations. And basically, we have 2 regions with nice boundaries. So this would be an illustration of disjoint regions in R2, partially overlapping regions. Here, the smaller guy is part of the bigger guy. Here, the bigger guy has the smaller guy as part. And here we have logical equivalence. So this means that one are part of each other, but they may or not be identical. So that's the basic story. And you find lots of theories about them. One of them, to formalize those ideas, is to use lattice theory. And then we have here, think of this as the intersection of sets. I couldn't find the nicer thinking. So if so here you have the number 1 or 2 is the intersection of R1 and R2 is non-empty. Here you have 1 or 2 if R1 is part of R2. And here the third bit would be 1 if R1 is a proper part of R2. So you have this idea that a triple of truth values is sufficient to define mereological relations. So if you have the relation of disjointness, then it corresponds to this pattern. And at this point, you have 5 relations. And here you have a gap, which kind of concerns the empty set or the empty region. So you have this pattern if the first guy is the empty region, the second guy is the empty region, both are empty regions. And those ontologists among you will kind of put up their hands. So what the heck is empty region? Right? So you don't do that. So, and the empty region technically is a placeholder for a regional entity which you know exists, so it can be named, but it's mereologically indeterminate, so you can't fix it on it, so you don't know it. So, and all of those guys are mapped to the empty region. So the empty region is a placeholder for entities or regions which are void of mereological information. Okay. So now the question, I use information quite a bit, but so far I just told you a story about, well, there are certain predicates to be true, and those predicates, depending on the truth values, they pick out certain relations, right? And I asked you for a little bit inflexible this empty region to get sets of 8 relations. So, but I talked about information, and everything kind of relies on the idea that it's not just about truth, but it's about information. Okay, so what is information? So I understand information as information excludes possibilities. So in this context, I understand ontology as something which limits possibilities, right? Ontology gives you the limits, and the information within those limits tells you excludes possibilities. So let's think of a single example. So we have a coin world with a single coin. So the ontology of the coin world tells you that the coins has an up or down. So these are all possibilities now. So within this ontology, you can then make, you have your coin, and suppose you put the coin on the table and it is face up. So now we have, for example, the statement, the coin is face up. So if the coin is face up, then this thing is true. Right? And this statement carries one bit of information because it excludes one possibility. Right? The virtue which it attaches to the world, it throws out the possibility that it right? Okay. So the coin is face down is false, therefore carries 0 bits of information. And the coin is face up or face down is true, but it carries 0 bit of information because it doesn't include possibility. So this means that truth and information or carrying information are not the same, right? So it can be true, but only if you exclude possibilities, you can have information. And the intuition is the more possibilities that you exclude, the more information you have. Okay, so with this, let's go back to our example. And here we have the kind of makes a bridge between truth and information. So, so far I told you the story of we have those relations, we have those formulas, those patterns, put zeros and ones, interpreted as true or false, then pick out those relations. We have 3 formulas, each of them can be true or false. So we have 2 to the 3 possibilities equals 8. Corresponding to 8 relations, we get those empty guys. Okay, so that's what I had before. Okay, so now there's an interesting thing that we can interpret those truth values, not just as truth values, but as bits. right? So now we can, it's trivial in one, but it's kind of not so trivial in the other way. So there's 3 bits of information, right? 0, 1 bit, 2 bits, 3 bits, and 3 bits. This row has 3 bits of information because it excludes 7 out of the 2 to the 3 possibilities, right? So if you just look at the bit, as the first bit, the value 0, this has 1 bit of information because it excludes half of the possibilities. So this guy has 1 bit information because it excludes the other half. So we have this nice correspondence between truth values and bits of information. This comes basically from this idea that we organize this table nicely. So this, and this is very common in symbolic AI. So in ontology, we are interested in those trees, and AI people are interested also in those trees, but they want to have them nicely organized so that you can use your truth values as bits. So if this is an example, you can use the same for layer topology or whatever. If you have a set of jointly exhausted pair-by-pair joint relations, so you think of the leaves in your trees, then you can use the same. Okay, so here's for 2 more examples. So if you look at just 2 of them, then the pattern 1, 1 for the first bit carries 2 bits of information, 1, 2, and it includes 4 out of the, excuse me, 6 out of the possibilities. Right? Again, it's the same idea. So the more possibilities you exclude, the more information you have. Ontology gives possibilities, and if you arrange those possibilities nicely, then there's this kind of obvious match, which one almost doesn't seem between truths and determination of bits. So seeing those truths as bits will be important. So, but now we need to look at the fine print. So whatever I assumed so far, so I say that those R65 plus relations, so these are the Mereological relations plus the 3 guys you get as MP7. Carries 3 bits of information, but then we go back to my picture here. Whatever we're doing here, in order to get those nice zeros and ones, you really want to have those nice guys with nice boundaries. Right? So in order to have those nice truth values, you have to have the same boundaries. So as soon as you don't have those nice boundaries, things get ugly in the sense. So here you have, I use this example, it may not be the best one, but suppose a relation of Eastern New York and Western New York, right? So those regions, they are real, right? You understand what they mean, you roughly understand what they refer to. It gets more complicated when you think about the relationship between. So if you think about it, they are surely not equal. They're surely not part of each other. And probably if you think about it, your intuitions are that they're disjoint. But the intuition mostly comes from this east and west perspective of York here, right? So if you can imagine if you are at the boundary of time, so then it may not be so clear whether or not they may be partially divided. So stick with me for the example. There are examples, but I wanted to use this one. So we can agree that whatever it is, it's either this or this, right? So, and we can assign because those boundaries for Western New York and Eastern New York, they are not this kind of boundary, right? So we can't make it. We can make it crisp by fear, but unless we kind of get a law pass. You don't get this. So this means that when we go back to our table, that if you look at it semantically, it finds your friend, then you may think that you have a truth value gap here, right? So that there are certain cases where you can't make truth determination. Or alternatively, you can say, look at kind of more ontological view in the sense that, well, those regions are such that you can't have 3 bits, right? You can't have 3 bits of it. And this is the central claim on which anything hinges. So if you believe that if you have vague regions, so look at if they are crisp, you have 3 bits, right? So that's not arguable if you look at pairs. So if you believe that for regions which are subject to vagueness, if you believe that for them you can have less than 3 bits, then you end up in the quantum theory. So that's the only problem. So, so I believe that this is a reasonable way to think about this. So, but you may not. So for let's just stick with the supposition that vagueness expresses itself, mereological vagueness expresses itself in virtue of, in the crisp case, you can have 3 bits. In the vague case, you have less than 3 bits. If you believe in Cat fine, I think your community will say that you have less than 3 bits. So the question is, what are the consequences of that? So if there are 3 bits of mereological information for crisp order pairs of regions, and there are fewer than 3 bits possible for regions with indeterminate boundaries like W and Y and Eastern and Y, then mereological information about regions with indeterminate boundaries will be quantum. And again, don't take my word for it. There are theorems. And it basically goes back to the Heisenberg's uncertainty concept. So the Heisenberg says that if there are limits of the amount of information you can have between objects, then this whole thing of quantum. And so historically, we focused more on the physical manifestations of why this happens with laws and but it's logical, mathematical, nothing that we do with physics. So if we believe that, then in the whole apparatus of quantum mechanics comes in. So the question is, why would it look like? So here, let's start with the usual way our physicists use this. Right. So if you have a classical theory where you have 2 possibilities of value, which is true or false, you go to a quantum theory by making all of the values you have into their corresponding Hilbert space. So the Hilbert space doesn't do much. So the idea is the following, that in the classical case, we work with those 2, right? So 0, 0 was this drawing, 1, 1 was mereological indeterminate. This is, I think, partial. So when we go to quantum formalism, then each of those relations, so this drawing, blah, 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 becomes the basis in a vector space, right? So this means that we have a 6-dimensional, 8-dimensional space. Those spaces that right, these are the x's, the y's, and z's in 3-dimensional space. And each state becomes a sum of all those spaces. Right? So you have your original relations, for example, the straightness, this guy becomes 1 and everyone is 0. But you can also have superposition stuff, right? So you can have the relationship of disjointness and partial overlap. and so on. So in general, so these are the basis vectors of vector space. And the idea is that whatever is possible here, so we have to say there are of course infinite different things here. But so there's a finite number of nice vectors or compositions here, which will be our vague relation relations. And again, if you pick out the basis vectors, this will just be the class. So those numbers, those coefficients here are probability amplitudes. And these are basically how likely it is that you see certain relation. So again, the classical case, 1 is 1, and the other 1 is 0. So you are not likely to see the correlation. So now let's see what it will look like for our two regions, right? So in this formalism, this we couldn't exclude those two possibilities. So, but everybody else was excluded. So only the destroying vector and the partial overlap vector will be non-zero. And since we could make up our minds, we have the same coefficient here, which we interpret as the equally likely or the equal superposition of state. So the question is now, what the heck does it mean? Clearly, you can't be at the same time as a classical differential. But here we have vague regions, right? So the point is that it should have made it. So we don't have this picture, right? So these boundaries for those two regions are not like that, right? So that's why we can't distinguish that. So the idea, this formula is that if you're interested in knowing exactly where that's from your begins and ends, since these are field objects, you can make it crisp. Right? So in the same sense in which physicists make measurements, you can make, or humans can make field objects crisp by making boundaries. So here it says then, well, if you take an arbitrary observer, then there's half and half probability that you choose this or this. So you may not like the half and half, then they put the probabilities. But that's the idea, right? That before you do the crisping, field objects can be into superposition states which basically says that if you make the thing crisp, these are the possibilities you have. You can do that, you can do the other one, and in this case, which one? So again, so this is something you can test. I'm not saying that I tested it, but there are hundreds of tests. So if you believe that, then you can do then you can put this formalist into work, and it will give you a whole bunch of states, which then you interpret as relations. And then you have, for example, the superposition of being part of or having a part. Right? So that I think of it as being the state of the nest. Right? You know that they are nested into each other, but you don't know which one the bigger one is the smaller one. There are lots of this. Okay, so this is basically the story of, so if you believe that there are 8 crisp relations for which you need 3 bits to represent information, to encode information. If you believe that in virtue of the vagueness, the vague region, because of vague regions, you can have 3 and less. So you committed to quantum information. And if you're physics background, in physics, then you should choose this formalism in order to spell it out. So again, this doesn't mean that you have to have a quantum computer or that you can just do maths, right? But the formalism is the same which you physicists use to talk about atoms.
But how we have superpositions of probabilities. Where does the case come in? Where's the complex? So it comes from Heisenberg's insertion.
Yeah. Well, I'm here. Well, I choose a nice place. So I have presented in a nice way where all of the coefficients are even numbers. But you could use other ways. Oh, yeah. Okay, so, and I'm not going to details, but you will have to explain what it means. And again, I can tell you a story about it, but that's not. So I give you an intuition in a second. So, but suppose you are an ontologist, so you probably like symbolic AI, and you don't like complex numbers. So there is an alternative way of doing this, and this goes back to this many work. So yes, it's relatively recent, but he's not 5 or 6 papers. And this establishes that you have a one-to-one correspondence between particles of a set of two-to-seven numbers and the quantity state of quantity system. It's one-to-one-ish because then the Hilbert space is much bigger. Right? But so you have this correspondence, and so this means that it may be better if you do Mereology and talk to philosophers to not to use the Hilbert space formalism, but to use this alternative thing. So doing the Hilbert space analysis, so I know that there are 48 relations which correspond to certain quantity states, which I showed you earlier, right? So you have significant more relations which come into two matrix. So then the question is, how do we spell this out in terms of those partitions? So first of all, there's a problem, right? So here we have 48 relations, and I was surprised how many partitions a set, yes. So I always said the set of our subsets is big. The set of our partitions is huge. So if you have 8 members, you have 4,140 partitions. So lots of what quantum mereology in this context means is to get rid of most of them and tell a equivalent story of why it is so. And this is in a way like physics. So what you're doing is you find partitions which remain invariant in a certain transformations. So you find basically you're trying to find a geometry of the information space. So you take the bits, and they are not just partitions, they also, you can think of them as the vector space. So let me give you an example. So remember that this were our table we started from, and we have those pattern of bits, right? So to kind of think about those bits as an information space is all just the Reason's call. Of course, if you want to do to tell a more sophisticated story, but the basic idea is these are not just bit patterns. You can think of them as coordinates. You can embed them in a 3-dimensional space, and then you have your coordinates, right? So so now you go from just bits to a thing which has much more structure, right? So something which knows what a square is, right? Something you can rotate. And if you rotate it, whatever is an edge or a plane here will remain edge. Yeah. Okay. So so in the same sense, then you have those single bits correspond to those planes, and you have left, right, front, back, top, bottom. So this would be the superposition states. And those, but in the Hilbert space formalism would be entangled space would be those imperial points. So they look weird, and they should be weird because those entangled spaces are weird. But the point is, you can have a geometric language where you can kind of tell a story what these things are. And it's all in this information space, right? So these are things with coordinates, these are planes, these are lines, these are geometric objects, right? So, and so this would be things, this plane is 1 bit because it forms a partition. This guy is a partition, the plane. Another way of partitioning the plane is a cube. Another way of partitioning or the sets of relations. So then you can have 2 bits. So each partition then has 4 possibilities. And so those are the tangled guys which will behind. So then you can show that this whole thing forms nice hierarchies, right? You can then do this thing. So then you have this partition in those 2 planes. It's this guy, so this guy, let's be this guy, and so on. So, and then you can have a story. So that's a space of the information space of possibilities. This should remind you of this hierarchies we did with the kernel partitions, right? So it's a little bit more complicated because it's bits, it's not just chunking up space, but it's the same idea. So what I did is you can build a whole framework about it. So nothing is, but I said it's limited to 3 bits, right? You can make it as many bits as you want. So if you do R16-8, which will put the topological relations, they will just have more bits, same ideas. And what you have to do is, and you have to tell a story, right? So you have your classical bits here, and then there's in the same sense, when physicists quantize theories, they start with the classical one, whatever is a variable which has numbers, we throw out to replace it by an operator. Right? There's a kind of systematic heuristics which you do to quantize theory. So the point here is this picture kind of illustrates the paper the way you quantize list theories. So in the way you could quantize inequality. So if you believe that you need vagueness addressed in terms of information, then this picture tells you how you use a quantization, and this is spelled out for the again, so what I'm briefly, so I'm going to go quickly. So nothing hinders you to go bigger than this. What I did here, you do all the time when you do those classification trees. You just would say these are non-normalized ontologies, right? So you would say that this is ugly, we don't write this, so we write it specifically in 3 different trees, and then we have the reason to the combination. The point is, whenever you have process information, then you will have those trees. Those trees have n leaves, which means that you have particular index of information. If you can't have them, then one kicks in. Just the last thing is, this would have to be tested, and I'm working on testing this. If you look at the stuff they work with neural networks, then a core idea is that you take the world, so it's a Boolean expression that makes it into vectors, right? And then you do different vector spaces in order to make the things split out of the next word. So in the sense that you have king minus 1, man plus woman, it's roughly the position of king or queen. So the idea is that you have categories which are places, and you have relations which are And so the point is that that's what we do when we go from a classical logical theory, which thinks in terms of true or false and categories, we go to vector spaces. So it's a fancy vector space, but it's the same kind of thing you do when you analyze those neural networks. Right. So so at the moment I'm looking in, suppose you train a neural network about things like Western New York and Eastern New York State. So the system sees some probabilities, right? Those neural networks are inherently probabilities. And so the idea is that you can make predictions about the probabilities you will see. Those predictions basically are kind of partitions, and this is the way you can test it. So one consequence of this is if you believe that, then you make all your neural networks with complex numbers. Okay, but questions? Yeah.
I have a comment, first of all. So it's odd that you chose the example of Western New York.
Yeah,
Because in 1664, King Charles II granted the Duke of York a large amount of land which stretched from the Atlantic Ocean to the Pacific Ocean.
Mm-hmm.
That was New York. Gradually, they made it smaller. Originally, it didn't.
Right.
The Western New York was much bigger than now.
Mm-hmm.
And I would imagine that there is a sense of vagueness which concerns where, at that time, New York really ended. The government didn't reach, the authority of the government didn't reach out to the Pacific. Anyway, that's just it's an interesting example that you chose because it's more complicated than so you base a lot on the idea that if there is an equal possibility that you get a response to the question of the relation between Western and Eastern New York, that they are either overlapping or disjoint. I think you would get neither of those responses. The response you would get would be, it's vague.
Well, that's an empirical, but I'm not
So we
saying
can test it here if you like.
well, so my point basically is, so what I'm trying to illustrate is the given way of thinking. So I'm not saying that it's true in the world, right? But it makes predictions which can be tested. So your intuition may be right. So that's not, it's a possible world, but it's not ours. So maybe you're right. So well, I think it's interesting, and maybe those. Yeah, well, but so we are trying to thinking of those kind of eight relations, right? So suppose there are more relations which you can choose from.
Didn't you yourself publish a paper on Mereology?
Well, you stole the name big, so I couldn't be doing name topologies. I couldn't. So I use approximate.
Oh, yeah.
Or something. Yeah, no, so that's why I use one time. But it's more about the quantization. It's not
Yeah,
Chinese way.
Really interesting. This is is there anything special about mereology other than it can be represented by 3 bits? Can anything that's represented by 3 bits have the same argument?
In principle, yes. So the ontology, the mereology comes in the story what's true or false. All right. So as soon as I talk about bits, it's all the same, right? So and the connection to the so what the partition does just is a trace of identity matrix of the pure sense. So that's the
Is this related to the very small area of quantum natural language processing? Have you looked at that? Thinking of that?
Well, I haven't looked into all of these things. So there is some literature. So the idea is that, so people agree that in neural networks, well, in general, words become vectors, right? So and then you can use linear algebra to think about relations between vectors.
So there's some work from the early 2010s, before neural networks were
Yeah.
the big thing they are now.
Yeah, actually, this is the Queen example is from the same.
It's looking at from 2019. visual-
Oh, maybe, yes.
Yeah, but from early,
Mhm.
that, coming out of Oxford on using quantum computing to try to do something better. This is again before neural nets took off more than they do now. That looks a lot like some of the examples you were trying to bring. And so.
Right.
We're looking into.
Right,
And I know they're still active, like I just looked up, they're starting conferences today, so.
right, right. But again, there's a distinction. So this is more like doing physics than like quantum. So again, it's you can use the same formalism or look at the same different aspects of the same formalism. You have to do lots of stuff. In the same sense, you can use set theory to use zillions of models, right? So they all use curly brackets, or they all use cat vectors.
Public spaces and quantum exist
Right.
to understand how language fit together in art, so I like what you're talking about.
Yes.
So I think there might.
Yeah, no, you can send me the reference, yes.
Other questions? I have one.
Mhm.
So you use the Carnap-Bar-Hillel account of quantity of information for propositions. And I was wondering because like there are some limit cases, so you have more information if you exclude possibilities. So a contradiction would have maximum information that is a bit perplexing. And in the case of applying these two ontologies, if something is like heads and tail up, so a contradiction would be super informative as well as being a quality and an object and a process altogether. So have you considered these limit cases?
No,
Okay.
you can send me a reference.
Yes, and I can give you another problem. So it seems you
Well, but
give-
it's problem, so. Can you explain?
because you want to model something in natural language, in common sense, it seems that some propositions, true proposition, and maybe even false propositions are more informative than others.
Oh, okay.
Okay, and you want to model these with basically the basic connectives and the truth of the propositions involved here.
Mhm.
And you say you exclude possibilities, so you have a series of conjunction, for example, and let's say you have a contradiction instance, so you have a false, and you can have, of course, all the propositions false, just one, you can have all these kind of combinations. Or in the case of this coin, is the head is up and the tail is up,
Mhm.
would be a four possibilities actually was not in your slide and would be maximum informative given your account.
Yes,
The
but
more
it would
you-
have, it would be false,
Yeah.
right? So it doesn't have information.
Okay, so you can add to this system that if something is false, it's not informative, but you have to
Yeah.
limit this case. Second, it seems this account is also tackles complex propositions, but it seems still here in natural language in common sense that atomic propositions can be more informative than other atomic propositions. I give you an example. Penguins are animals,
Mhm.
proposition A. Proposition B, penguins are birds. This seems more specific. And of course, we know because in the ontology tree of biology, birds are under animals. Fantastic. But you seem not to be able to represent this distinction.
Yeah. Well, my basic, so again, I'm not in natural language processing, so I
Me
don't know.
neither.
So, but you seem to know the literature better than I. So the idea here is that you have one of really fundamental relations, right? So if you look at, oops. Can I? How do I?
No, it's not. Just there.
I'm stuck here somehow. I don't know. So the idea is that if we talk about the Mereology, so maybe put it this way: not any old proposition will do, right? So we have already said so what he addressed in the sense, right? So there's a difference. So you have to be clever to choose your proposition nicely so that you can kind of link those truth values to bits in a way which doesn't give, right? So you can do it in each old way, right? So and when you do those AI people, you always have those kind of typical tables, those joint exhaustive pairs, disjoint relations. So you put lots of work into findings and finding the right ones. So and words, and so you wouldn't have nested categories. So you go automatically to the lowest level, and that's why I also focus on the leaves of the category, right? So I didn't talk about things in different. In the theory, the formalism probably could do it, but maybe there are no reasons not to do it. So I don't know, but so there seems to be an interesting relationship between ontology, which makes the possibilities, and kind of choosing how you go from truths to bits. So this doesn't seem to be trivial. Yeah, I would agree on that.
Okay. Other questions? Okay, let's thank our speaker.